What's going on, everyone? Welcome to Digital Wildcatters Power Hour. Got a very interesting topic that we're talking about today. We'll wait here a few minutes to let some people get in. Blake, Robbie, appreciate you guys joining in today. I'm excited to do this and learn something. So thanks for taking the time to do it.
Thanks for hosting us.
Yeah, absolutely. Blake, you made a comment the other day that you were excited that you got to be part of the cool kids and on Digital Wildcatters. So we were laughing about that when I told the team.
That's not the case. I thought that was true. This is the cool kids in energy tech.
Yeah, absolutely, man. So, all right, let's frame up what today's conversation is going to be. We're talking about causal AI and the applications that it has in oil and gas. And, one reason that I'm really excited to talk about this is, AI is all the rage today. Everyone's talking about it. And, most of the applications are in language models. Chat GPT is taking over. But I think what's really interesting is the way that machine learning can be applied in heavy industries, specifically oil and gas and energy. And that's what Senslytics is working on. And you guys are the experts on this. So I think that it's going to be a pretty interesting conversation, to say the least. So Blake, real quick, do you want to give us high-level overview of what Senslytics is? And then let's start diving into the topic.
Absolutely. So first, I've got to say, this is all technology that Robbie has developed. He's got we've got 6 patents, and he's developed all these. These were all his concepts and all his brainchild. But what Senslytics is a causation-based AI software platform that can be used across many use cases. And so it's basically a platform that can be adapted to different situations. And the goal is to always figure out what the cause of a situation is. Because if we understand the cause, we can predict what's going to happen better. And then if we know the cause, we're also going to be able to explain things better. So reduce the black box that's out there. And I think where we really see the value of this is there's so many instances in AI where it can give you nice probabilistic predictions. But what happens when the stakes are really high and you're like, I can't have a failure on this event or on this asset? Saying, well, we're 90% confident is nice, but you need to know very definitively. And so you need to be able to determine the cause.
Yeah, especially in this industry where, that 1% where you're not confident can cause pretty extreme damage, both in terms of economic damage or life and death in some situations of personnel. And, I was looking up, just the quick Google definition of causal AI is it can explain the cause and effect of different decisions. And so to me, it kind of seems like, all right, this is an application of where it can, give you these outputs, but then also explain and within context tell you, the why behind it. So let's dive into y'all's presentation, and I will ask questions from the viewers as we go. So if you're watching, feel free to leave a comment at any time, and I will ask Blake and Robbie questions for you.
So thank you, Colin. Thank you very much for inviting us, and we look forward to this webinar. Blake, you explained the causal AI and the way we are looking at it quite appropriately for oil and gas. So look forward to this conversation. Thanks.
All right, we'll dive in. So most of what AI has done to this point is based on finding correlations to make predictions. And the more data there is, the more complicated the method of correlation becomes. So we've got a couple of fallacies on this page to illustrate the importance of getting to causation rather than simply correlation. So on the left-hand side, you see that you clearly should not be eating ice cream before swimming in the ocean, or you're at risk of a shark attack. Or at least that would be what correlation would show. Obviously, we know better. We know that in the summer, it gets hot, and so people like to eat ice cream, and they also like to swim in the ocean, and that's why those things show similar curves. The right-hand side is a fallacy that I fell for. Shaving my head did not actually increase Senslytics sales trajectory, but it's a startup. You got to try a lot of things.
I thought it was the Mr. Clean look that definitely sold y'all's company.
Yes, exactly. Thanks. Yeah, so those are some extreme examples. It's probably important though also to kind of get to how do we get to this point? So kind of walk through a little bit of the timeline. So the basis of correlation is statistical regression, which is things that a lot of people may have done in classwork in college. But the first machine learning came about in the 40s and 50s, both supervised, where you train it on data and you're telling it yes, no, unsupervised, reinforced. But there wasn't that much that could be done with machine learning until big data became available. Then you could start to do some great correlations, detect anomalies. Requires a lot more computing power, but a lot of times it was worth it. So 2005-ish, neural networks kind of came to the forefront. And if there's any data scientists out there, we're talking about this more from a standpoint of when it came to industry as opposed to when it was developed. So because I know a lot of people know these things were developed earlier, but they weren't usable because we didn't have the computing capabilities. And we're focusing here on things in industrial applications rather than, like you said, the chat GPTs, the language processing, generative AI type things. So neural networks allowed AI to think a little bit more like a human brain. It needed a ton of data. And like we talked about, it was still a black box. Like it might give you a better answer. You don't know why though.
Mm-hmm. So I think this is pretty interesting. Let me pause you real quick because a lot of people around the world are becoming familiar with AI, and even if you look at OpenAI and ChatGPT, I mean they've been working on those models for 7 or 8 years now, right? And this is based on decades of evolution of understanding. And I think that it's interesting when you look on your timeline right here in the 2000s, you have big data widely available and then moving into neural networks. And so there's a couple of things that have allowed us, I think, in my understanding of y'all's timeline is one, having big data sets to train these models on. And then also the advancement of GPUs and computational power to run these big models. And so it's probably, there's probably several different factors based on this timeline that have allowed us to get to where we're at today.
Absolutely, Colin. You had the computation power, the hardware piece, you had the cloud concept, you had the networking, you need the security, you need the access control, all those things had to develop. And they were all precursor once internet came in and those technologies got built. Boom, there you have the magic,
Yeah. So, physics-based modeling, can you dive into that a little bit and explain what that is, Robbie or Blake, whoever wants to explain that to me?
Robbie, I'll let you go ahead and take that one.
Okay, sure. So if you think of physics, theories are very complex, especially if it is in the atomic level, molecular level. So a lot of time you do not have the luxury of doing something that is experimentation, straightforward experimentation. Even if you do some of it, they're extremely expensive in the, for example, plasma science domain and concepts like those, right? So you needed to have a tool that would be able to give you what if scenarios. So simulations came in picture. But the simulations are built with understanding of science. So physics-based modeling is typically driven from simulation and then how data sets could be regressed, correlated, extended, iterated, stuff like that. So its foundation is that.
Awesome. And then, I thought it was interesting when we connected with you guys and started learning about causal AI because it's not something that I hear about a ton, with the wave of AI. And the reason that I'm excited to be able to talk to you guys about this and learn about it. So talk about, you have it here in the late 2010s. This is kind of when it started becoming a thing. Talk about how that evolved.
Robbie, you were right there on the ground level. So go ahead.
Okay, Blake. Thanks. It's a good question, Colin. So, correlation models were black box models, and many times they do give good understanding, especially if the causation is equal to correlation. For example, you press a brake and the car stops, type of thing, where the time difference is not there much. You can get by with causation in a lot of cases, and it will be proved to be a causation with correlation itself. But sometimes we go drastically wrong with that, and the predictions give you wrong results. Fatality happens, lots of heads roll, and then people say, hey, what is your model is completely failing us. So as we started realizing correlation isn't causation, let's understand explainability, let's understand going inside the black box. So the effort has been going on. I would not say anything started in a particular day, but all the researchers around the world started coming together to this understanding that we need to somehow link with these data sets what is before what causes what, how can we uproot rule out the problems that are not connected, somehow like that. So yes, now it is the time of causal AI, and we are in a unique position inside the causal AI itself. So
Yeah, I think that's really, it's interesting when you think about the applications in oil and gas, as we kind of alluded to earlier, that, when something happens in the oil and gas industry, say like a pipeline leak or a well blowout, these are always the 1 in a million chance that may be an outlier in the data. So why don't you guys, why don't we move on and y'all start talking about how this actually works from a conceptual and technical perspective?
Yeah, absolutely. So just real quick here, when we're talking about AI, causal AI is a form of AI, just like generative AI, like you see Chat GPT. When we say intuition AI, we're talking about Senslytics proprietary platform. So just to do a little bit of level set there. But they're, neural networks, physics-based, like we said, many forms. And just so, Colin, just to refer real quick, you said you don't hear much about causal AI. So this is the Gartner hype cycle, and you see where causal AI is at. So it is just getting up this hype cycle. It's just showing up. So they project this as to be in a 5 to 10 year time frame to kind of fully be capitalized on. But it is a new up and coming thing.
Always love watching the curves of hype cycles and seeing where we're at.
Yeah. So causal AI, like at the very basics, there's a few different ways that it's done, but they all kind of come back to these four things where you're finding an association. So you want your output to vary with your input. And from that, you're trying to find where the potential causes. Obviously, the cause has to take place before an effect. The delay between cause and effect can be really difficult to establish because especially the things we're talking about in energy, where you've got chemical, geological, biological systems, there can be a varying delay in that cause and effect. And that is something that's really hard to find, but that's where you really need causation-based models because correlation is not going to pick up on that if it's highly variable. So then the next thing that they go to is ruling out inputs. You want to get rid of as many rival explanations as possible so that you're down to the few things that really matter. And then you're determining the cause. And it looks quite simplistic on this diagram. It's obviously the coding and the building of the models is much more complex. But so there's a few ways of doing this. They developed physics-based causation models, statistical ones like deep learning. All of these still need big data sources. Causal graphs, which are basically looking for like hard and fast relationships. The thing is, if something is one thing one time and caused by something else another time, it kind of struggles. And so we're in a new bucket that's clear on the right, which is hypothesis refinement. So we are a hybrid data hypothesis iteration method of getting to the cause and getting to the interpretation.
So at the bottom of that
Sorry.
slide, real quick, go back real quick. The modeling techniques and the logic down here. Can you explain that to me a little bit?
Yeah. So just a few different ways that cause is causation kind of happens. And actually, one of the places where you might have encountered this is you may have had an English teacher or professor at some point that said you've got to write about cause and effect and the different kinds of cause and effect. Anyway, so common cause basically means that one thing causes multiple other things. So we go back to the kind of the example at the beginning. A hot day causes ice cream sales to go up and lots of people to go swimming. Multiple causes. That's where we get into something like the 08 financial crisis or something where people say it's a perfect storm. A and B and maybe some other things happened to cause C to happen. Chain reaction, probably something people can envision pretty well. Just, the first domino falls, then the second, the third, and so on. And then cycle is kind of, depression would be a good example of that, where you're just going back on a loop and kind of spinning more and more down whatever hole you're going down.
Mm-hmm. Great, thanks.
So I'm going to talk just a little bit about Senslytics and what we're doing and what we're doing with causation-based AI. So for geological and biological and chemical systems, lots of times you have limited or noisy data. And so then it's pretty hard to train a model that needs big data. In fact, you can't do it. You've also got the varying delay between cause and effect that we've talked about, and then the need for a definitive answer rather than probabilistic. So you've probably heard it said that a picture's worth 1,000 words. For us modeling, one subject matter expert hypothesis is worth 1,000 data points. And so this is how we're creating the model. We are making use of the subject matter experts and their knowledge, codifying that knowledge and putting it into the model so that we can understand things much better than you could if you just had to do simple correlation. And those hypotheses can be anything from empirical formulas to something as simple as, if you're in an oil and gas reservoir and you're going up the pay zone, higher in the pay zone is going to have lighter hydrocarbons because they migrate towards the top. So, whole variety of complexity that can go into those hypotheses. But that's what helps us create the map. And then what we're looking for are those unexpected things on the tail end of the distribution curve. So when you're in the middle of that distribution curve, it's kind of business as usual. This is where somebody designs an AI model and they show it the subject matter expert and they say, tell me something I didn't already know. Or maybe, optimization just isn't that valuable. If you do something 1,000,000 times, optimization is really valuable. But really what you're worried about is, where are things going to deviate dramatically from what we expected? So like if we have corrosion in a pipeline, if it's growing at a constant rate every year, you kind of know what you need to do and where to expect it the next time that you inspect that pipeline with like an inline inspection tool. What you're concerned about, though, is that every once in a while, that corrosion starts to grow exponentially. And then all of a sudden, you've got a leak, a rupture, or an asset that's got to be taken out of service. And how do you predict those? And so that is really what we're trying to get to. And there's not enough data out there to train a model or a correlation-based model.
Yeah, so it's fair to say that causal AI, looking at your distribution curve here, you're really solving for the tail ends of that curve. Is that kind of a fair assumption?
That is what we are doing. Other methods of causal AI, some are working on this, some are working on optimization problems. Believe it or not, some of the easier places to adopt this and where some companies have had success have been things like customer churn. So like what customers do you need to talk to more frequently, or what actions do you need to take with them so they don't leave? That's still more probabilistic. And you can get to big data there, but it's still causation based.
Yeah, so it's a very good question, Colin. So people have different motives here. Okay, so causal AI is useful to some people where there's a ton of data, but the insights are not enough. So you are trying to find the root cause from millions of records. And for that, the distribution, which is the frequency distribution that is the middle, the green ground, is very useful. But the problem is that is machine learning techniques. It needs lots of data. The problem is if you don't have those data, okay, and almost always all these things that are not so frequent are of maximum value. We do not look for collecting sand. We go after gold because it's rare. Okay, it is important that we need to know if there's a heart attack going to happen. That's rare. It's not an everyday thing. So when you look at where the focus should be, where the science strives to go, is to find those unknown characteristics, find those unknown reasons why something rarely happens. I'm not denying that there is value in the middle ground. Of course there is. But because machine learning feels helpless here, this is sitting quietly there for a long, long time.
Yeah, I think when you look historically in the oil and gas industry specifically, AI has always been really interesting, but the problem is that you don't have these big data sets or high quality data that you can train models on of repetitive actions. And so it's really how do you utilize artificial intelligence to help predict things, to help things become more efficient when you don't necessarily have extremely large data sets or repetitive actions with, a low percentage of variability. And so I think that, that's been something over the last, call it 5 years that people have really been trying to wrap their head around.
Because you are on the context, Colin, very good point. I just wanted to say one more thing. A lot of times, you do not have the ground truth right then in oil and gas. It's a very interpretation-driven investment. So you are drilling, hoping to find a few feet of pay zone, and you are drilling 30,000, 40,000 feet. And you invested a ton of money from the seismic data collection to everything else, with the hope that you will get a decent amount of pay zone. Now think it's almost like finding gold, right? So you're going down. Instead of gold, it's black gold. But the point is that here you have to interpret properly. So de-risking interpretation when there is not a constant feed of truth is a major problem. And oil and gas industry faces it almost every day. So with a hypothesis, we already build a fabrication of a scientific tool, to predict, and then we refine it. Sorry, just continue, Blake.
That was a great point, and I think that something that's really important in the context of this conversation.
Yeah, and so I'll say the use cases can be a little harder to find in this sometimes. Like some of them are fairly straightforward to find, but some of them are just places where people have gotten used to dealing with the problem. It's just like a fact of life. And so one of the things I actually want to encourage the audience to do, if you have a use case or something you think that somebody needs to take a look at, put it in the chat. We will send out a $50 Amazon gift card to whoever comes up with the best one. We'll notify you tomorrow. So we would love to hear your use cases, because we sit down with customers all the time and hear, well, have you thought of this? Have you thought of this? And there are things that we weren't even aware of, the size of the problem, or that the other methods of artificial intelligence weren't solving the problem. So next what I was going to do is just kind of show maybe pictorially a little bit about how typical artificial intelligence works, and then what we're doing with the hypothesis mapping and what that looks like. So if you see on the left-hand side here, like this is, it's a very basic rudimentary, but some level, every AI model has got some level of correlation that it's doing. And so it's fitting a curve to data. The thing is, these outliers, they're considered random and unexplainable, and they skew the data, so they're thrown out. But in natural systems, and the things we all deal with in energy, there are no such things as random events. There are a ton of things that we don't understand, but they're not random. So on the right-hand side, you see how intuition AI. And so these different situations are made up of expert hypotheses that we've tested for accuracy and bias. And so what we see is that these blue dots aren't part of one situation. They're part of 3 different situations. And we can see as one situation progresses that we should actually expect what was previously defined as an outlier. And we can even come up with a hypothesis for when we should see, these other outliers on the right-hand side. And so for us, it's all about getting an understanding of the whole box. That's what we're trying to do. Not just cover the middle of it, but cover the whole extent. So I'll show you just quickly what this looks like if we add new data points. So you see these green dots here. Say these are 3 new data points that somebody gives us for the model that we've built. And we're running through these and we're trying to make an interpretation. So can we interpret this first new data point, the purple one at the top? Well, it falls along situation number 4. So yes, we've got that mapped. We understand it. So let's go to the bottom right one. This one's a little more confusing. It's a little more out in the open. What can we do here? Well, in this case, we've got a situational rule. We need to see, like, have we hit the end of it, or can we extend it? And so if we say, yes, this situational rule can be extended, like we're moving into the unknown, but it turns out that rule can apply a little further. So, okay, that one can be modeled. We go to the third one. Can we do anything here? This would be a case where our model would say, this is uninterpretable. I actually see that as a feature rather than a bug, because the things you don't want is false positives and false negatives. You don't want to go spend money where you don't need to, and you don't want to have an accident where you didn't think you had a problem. And so this would be a case where we'd tell the company, this is where you want your subject matter expert to dig in, or this is where you want to do more testing. We, though, refining this model, would go back to the experts and say, okay, what's happening here? What have we missed? And if we add a new hypothesis to the model, we can plug that in, and now we've got understanding. And you see, okay, we've moved to covering more of the map than what we previously could. And so that's kind of how we extend and build intuition AI at a very high level.
Blake, fantastic way of explaining it. Just wanted to add one point here. See, the beautiful thing is you can extend the model very easily. So I make a joke that if I have to drive a new car, I don't need to carry all the cars that I drove since the first time. If I do, I'll have to carry a whole fleet. And that's what ML does. It needs all the data. So what we are doing here is we are internalizing the knowledge, transporting to a new situation. We may have to adapt to the situation. We may say it's uninterpretable, but we'll learn quickly. So it's not data driven. I don't need billions of data sets because I learned it. Our human mind also learns it. And the way we learn is whatever has been common sense, like general trained, it's going to be a common sense for us. We don't focus deeply on it. But whatever is rare, unique, we kind of like grab onto it. Don't forget it. So experts hypothesis iteration based modeling is a new technique that we are trying to come up with. And it could be applied for a new type of unknowns to find quickly.
So Colin, I'm not able to hear you right now. Sorry.
Yeah, I just pulled a boomer move and had my mic muted, so apologies about that. So on this slide, I'm curious about the ability that intuition AI has. So on this example, you show, hey, there's a situation 5 that fell outside of the parameters of the model and what it recognizes. And so does that model come back and say, hey, there is a scenario that we don't know what it is or how to fit it, and what action does it take? Because, I have kind of a funny story that I'll share here with ChatGPT on GPT-4 the other day is, I was asking it a question and I said, hey, I want to transcribe an entire podcast. How can I do that using GPT? And it gave me a few options. And one of them, it said, you can email me. It said that. And I was like, I can email you? How do I do that? And it's like, yeah, you can send me an email at chatgpt@gmail.com. And my next prompt was like, are you sure that I can email you? And it said, no, I'm sorry. I'm a language model. I don't have an email address. I can't do that. And so it had the confidence to tell me that it was kind of a weird conversation. It was kind of like it was lying to me. Right. And so that's where I'm getting at with these types of models is, we're talking about, let's say that if it's monitoring a pipeline and it encounters something that it doesn't fit within the parameters, how does it handle that? Does it just say, hey, we don't know what to do with this, and then you guys go in on the back end and figure out what to do with that data? Just kind of walk me through how that works.
Yeah, I'll give a very brief explanation and then let Robbie give a probably a better one. But so that's where the uninterpretable comes in, because we're trying to be definitive, and we're doing that. So we're taking multiple views of a situation. So like on a pipeline, we may have a metallurgic view, a chemical view, hydraulic view, several different views. We're looking for multiple sources to point to the same answer. And that's how we get away from being probabilistic. So when we've got multiple things won't point to the same truth if it's not really occurring. When those line up, we know, okay, we've got it. And if we don't have that, we say uninterpretable, because we've got to provide definitive answers for our customers. And so, like I said, we think it's better to say, we don't know here, than to give the false positives and false negatives. Mm-hmm. And so then we go back to the customer and we try to say, all right, what can we do to model this in the future? Robbie, what would you like to add to that?
No, Blake, you did it right. So multi-view convergence or confirmation is one of the ways to eradicate uncertainty in a probabilistic answer. It's the same thing that doctors do. You gotta check multiple medical tests before they can point out what exactly happened to rule out other possible explanations, as we say. So here, as I'm seeing, there are some questions coming up. Because this question relates to another question here, causal AI, how does it bring clarity to the black box approach? So, today we are solving a problem that cropped up by gathering tons of data that started from the database technology adaptation. We have tons of data today. We did not start collecting data in a causal way. We just collected because it's observations or some kind of information that came in. So we have this heap of data we are trying to solve. That's why causal AI, all the causal graphs, all the temporal precedence, all that thing is coming up in picture. But what we are trying to do is taking a separate approach. We're trying to build the fabrication itself scientifically. Scientifically, in the sense, you could have theory, you could have simulation, you could have guesstimates. It's a very big deal. I personally think intuition AI is experience mining of the experts. So instead of data mining, we're doing experience mining. It's a big deal. So much of knowledge is inside the people's head, and they are capturing rare events, in the things that are not frequently seen, because our mind gets heightened at those conditions, sense of uncertainty. So we observe very well. Somehow that has to be mapped out to a model. So the model itself starts as a scientific fabrication. I'm answering to the question of how does causal AI bring clarity to the black box approach? The model itself is scientific. Now you keep adding data to it and see what situation it works, what situation it doesn't work. Not everything is universal like E equals mc squared. It's a very important point that theory needs no data, and not understanding anything, correlation needs 100% data. What about rare events? Who is taking care of it? I think we are.
So, Robbie, can you maybe provide a little bit on the black box on what a customer would see? Like, so from their point where they're making a decision, what are we providing them so that they have, like, it doesn't just say do X, it says do X because.
Exactly. So, we have Shell, Chevron type of companies working with us, and they need to have recommendations. They need to be certain about. So anything, multi-view is a major deal for us. And we can see if a system, you are taking an electrical view of it, resistivity is changing versus fluid color is changing. So all those, so fluid dynamics is a view, electrical is a view. You have multiple views, right? Rigidity is a view, molecular composition is a view. You can come up with all these different views based on the use case. Now, some views will alter faster than the others. That will give you a lead time. You will know if this is happening, it's moving in this direction. Now we get other views. And once you get a convergence of them, we know we are heading towards the truth. We are very confident about it. And our use cases have been 100% time deterministic. So it's not probabilistic. Does it make sense?
So the thing I might add to that is, like, the customer is going to see something that pops up on the screen that says, okay, we are seeing that this feature is giving us the best definition of what's happening. And because this A is changing and B is changing, here's our interpretation of where you're headed. Either you're okay or you're about to have a problem. But it's going to pull out the factors and the logic behind, here's why there's a problem, here's why there's not a problem. So that then the expert can say, because we want to keep what we're trying to do is allow the experts to pull up to a 10,000 foot view instead of dealing with cognitive overload and trying to run from one fire to another. We're trying to help them say, here's where we need to focus our attention. So it'll say, here's the recommendations, and it's based on these factors. So then they can say, yeah, that makes sense with my knowledge, or they can dig in on those. Or they may say, I really disagree with that, and they can dig in further, but they know why, and they don't go do something and say, because the AI told me so.
Got you.
Is this a point to answer the first question? Was the process to fact check?
Yeah, we can answer that, and then I want to follow up with the last question. So if you want to answer that,
no, go ahead, Colin. I'll answer later.
Yeah. So someone asked, what are the future use cases that y'all are planning and excited about? And I know that, Senslytics has some specific use cases that y'all are focused on. And then there's a broader conversation around different applications as well. Do y'all want to talk about those real quick before we wrap this thing up?
Yeah, I'll try to be really brief. So I've highlighted the things under oil and gas. So the things in green are things that we've already done. So what we did with wireline formation testing as part of the Shell Game Changer program is basically help them analyze the fluid samples that they're trying to take before the probe has taken the sample. So basically helping them to know when that sample is clean enough that it can be taken or when it's not, and what actions they need to take so the fluid will clean up. The second one is mud gas logging, where we're taking data there is more of it, but it's considered low quality data. And we're trying to get it so that it's as close to ground truth as possible. So we've done this with gas oil ratio, where we've gotten within 3% on average, but 10% every time on the ground truth for gas oil ratio from a mud gas log. We're going to be adding API gravity and viscosity. Corrosion is what we're starting work on now. That's what we're really excited about because it fits all of Senslytics' unique capabilities with the time delayed cause and effect and the lack of data. And it's just a huge market. And then you see below some of those others are things that we're looking to tackle in the future. Where we have seen the most use cases that have already been tackled would be the kind of finance, marketing, and ops. This is because this has been where customers have been most willing to adapt it. If we want to talk about where is the big thing, what societal problems is causal AI going to discover or solve, I think it's in the healthcare sector. I think that is where the biggest societal benefit is going to come in.
Yeah, I think with that and pharmaceuticals can wrap up under healthcare as well. That's pretty interesting to think about. It makes perfect sense that it's already being applied and adopted in finance. Usually investors tend to drive any technological advances. So it makes perfect sense. In oil and gas real quick, just to touch on this a bit, y'all have done some of the wireline formation testing and open hole logging applications. I believe y'all have done, you're focusing on pipeline and predictions on pipelines too. Is that right?
On corrosion, yes.
On corrosion. Okay, cool. Tell me a little bit about that real quick, because I come from upstream, so I'm not as familiar with corrosion risk and pipelines. How does this type of artificial intelligence help with that?
Yeah, so really the issue there is that the data is not organized in a common way, or there's not a ton of data, and most of the time the problems, you might know you have some corrosion, but the big problems aren't discovered until a post-mortem. Because if you knew there was a big problem there, you would have done something about it earlier. But a few key things that we're trying to attack. So corrosion can be caused by microbial or non-living factors. And so if you think about, like, if you're a chemical company or you're purchasing things from a chemical company, it's like going to the doctor. And if the doctor can't tell if you have a bacterial infection or a viral infection, well, they don't know how to treat you properly. And so it's the same thing with identifying what chemicals to use. You need to know whether this is living or non-living forms of corrosion. That's hard to do until a post-mortem. The second thing is something that I mentioned just briefly before, which is, when is the corrosion about to take off and grow exponentially? Because if it's growing linearly every year, you're not happy about it, but you kind of understand where to expect you're going to be in 1 year, 5 years, 10 years. But we hear so many customers say, we had this incident over here where we didn't have a problem last inspection, and then all of a sudden there it was. And so that's why we've got to get to the cause and effect. And especially those things that they've just got a huge lag, like the microbial factors. Those things can lay dormant for a while until the situations are right, and then just start growing like crazy. And so
Interesting.
identifying the type and projecting the future growth rate, that's what we're focused on.
No, that's, I mean, extremely cool. You know, you talk about typically or historically, you can't identify these things until post-mortem. And at that point, it's way too late. So that's not the time that you want to identify that. So very cool stuff. Blake and Robbie, I appreciate you guys taking the time to talk about this. You know, it's extremely, one, I think that this is pretty cutting edge stuff, not just in oil and gas, but in industry and technology in general. And so it's really cool to see these things, you know, moving into the energy industry and finding applications and product market fit in certain scenarios and situations. If people are watching, they want to find y'all, what is Senslytics website? Where can they find you guys?
Senslytics.ai.
Senslytics.ai. Cool. All right. We will link to that as well. So if you want to get more information on Senslytics and talk with these guys, I'm sure they can go much deeper. Specifically, Robbie, I know I'm holding them back right now, not asking them the good technical questions. So I'm sure he can talk about this for hours. Guys, appreciate you taking the time to do this. And hopefully we'll get to chat more on it sometime soon.
Thanks, Colin. Thanks for having us.
Yeah.
Thank you very much, Colin.